They say the Big Bang created everything: space, time, matter, the very laws of physics. But what if that's not the whole story? What if the Big Bang wasn't the beginning, but the inside of something else? A larger structure, a deeper universe, a black hole? Now, thanks to the James Webb Space Telescope, we've uncovered a strange pattern: galaxies spinning one way far more than the other. A pattern that shouldn't exist in a random universe. A pattern that whispers of something bigger, hidden. This isn't just data, it's a crack in the cosmic code. Please like and subscribe, because this journey will change how you see our place in the universe. Prepare yourselves. We begin. It started with a number, not a theory, not a prophecy, just a number. JWST. That's how many galaxies, in one tiny patch of the sky, the James Webb Space Telescope saw spinning clockwise. That's how many spun the other way. This wasn't some ancient myth scrawled on a temple wall. This was light, raw, ancient light from galaxies over 9 billion years old. And this light told a story. The universe seems to prefer one direction over the other. And that makes no sense. Because in a truly random universe, a fair, balanced, unbiased cosmos spiral galaxies should be like coins tossed into the dark. Half heads, half tails, half clockwise, half counterclockwise. But they're not. The data came from the JADE survey, a collaboration using Webb's deep infrared gaze to peer farther and sharper than ever before. What it saw wasn't just beautiful, it was weird. From a patch of sky near the galactic South Pole, the team identified 263 spiral galaxies, clean spirals, far enough away that their shapes had been frozen for billions of years. But those spirals weren't evenly split: 158 clockwise, 105 counterclockwise, an imbalance big enough to be seen with the naked eye. And when you zoom out, when you think about what this might mean, it feels like something impossible just happened. Like a rule was broken. Like reality flinched. Let's slow down. What does it mean for a galaxy to spin clockwise? You're not watching it rotate like a fan. You're looking at its arms, the trailing curves of stars and dust spiraling out from the center. Depending on which side you're looking from, those arms can wind in one direction or the other, like two dancers twirling opposite ways. But here's the catch. From our vantage point in the Milky Way, we can't choose a neutral spot to observe from. We're trapped on a spinning spiral ourselves. We're not just watching the universe, we're inside it. And when you live inside a spiral, your perspective twists everything you see. To avoid human error, the researchers didn't rely on manual labeling. They used a tool called Ganalyzer, an algorithm that slices galaxy images into radial lines like a cosmic fingerprint scanner, and analyzes the brightness and slope of those arms to determine their spin. It's cold, objective, symmetrical. You can even flip an image and test whether the results reverse. If they do, the method is fair. And it did. So this wasn't human bias. It wasn't chance. It was something else. Here's where things get strange. If the universe is truly isotropic, meaning it has no preferred direction, this result shouldn't exist. The laws of physics should look the same no matter where you point your telescope. But this finding, it breaks that rule. It suggests a preferred direction, like the universe has a hidden spin axis, a subtle metronome, a pulse. And in physics, that kind of asymmetry is a big deal. It hints at something deeper than randomness. It whispers structure, memory, pattern. Some scientists believe this could be a cosmic illusion created by the motion of the Milky Way, our own rotation influencing how we see distant galaxies, like looking through a warped lens. But others? They're not so sure. In fact, this isn't the first time something like this has been noticed. Over the past 2 decades, hints of spin asymmetry have cropped up in other sky surveys. Hubble, Subaru, even ground-based telescopes. Some saw nothing, others spotted a pattern. The farther away the galaxy, the more likely it was to spin in a certain direction, a twist that grows stronger with distance and therefore with time. Which brings us to the big question: what if this isn't a coincidence? What if the universe has always been spinning? Not just galaxies, not just stars, but space-time itself. Enter the speculation. If the early universe had even the tiniest bit of angular momentum, a gentle cosmic swirl at birth, that motion could echo across billions of light years. It could bias the spin of galaxies. It could create dipoles, large-scale directional imbalances that we're only now beginning to detect. And if that's true, it might mean the Big Bang wasn't a perfect explosion from nothing. It might have been a rotation, a spiraling birth from inside something else, a larger structure, a collapsed universe, a black hole. This is where science meets imagination. There's a long-standing hypothesis, unproven, controversial, but wildly captivating, that our universe is the inside of a black hole, a 3D bubble of expanding space-time born inside a spinning cosmic parent. In this model, the spin we see today isn't random. It's a fossil, a leftover, a whisper from the universe before ours. Wild? Yes. Impossible? Not yet. And while this new JWST data doesn't prove that theory, it does open the door, just a crack, because the real shock isn't the data. It's the question it forces us to ask. If the sky is twisted, then so is the story we've been telling. And maybe, just maybe, we've been living inside a deeper mystery all along. A mystery where up and down, left and right, time and space aren't what we thought. This is just the beginning. Next, we'll explore how symmetry works in the cosmos and what it means when that symmetry breaks. The universe was supposed to be a mirror. That's one of the oldest assumptions in modern cosmology, that there is no cosmic left or right, no privileged orientation, no hidden bias. Spin a galaxy clockwise or counterclockwise, it's all the same in the eyes of physics. Symmetry reigns. It has to. But what if the mirror is cracked? What if, as we stare deeper into the cosmic past, the reflections begin to tilt? What if the spiral arms of galaxies aren't just random whirls of stars and dust, but whispers of something directional, something hidden, something true? Because symmetry isn't just an aesthetic in physics, it's sacred. The sacred code of symmetry. Symmetry is woven into the fabric of every major physical theory, from Newton's laws to Einstein's relativity, from quantum field theory to string theory. It's the reason why conservation laws exist. Energy, momentum, charge all emerge from symmetrical rules of the universe. Break that symmetry, and things start to shift. Laws become exceptions. Constants begin to fluctuate, and the illusion of balance gives way to a deeper, more primal chaos. So, when astronomers found that 158 galaxies spun clockwise and only 105 spun counterclockwise, they weren't just noticing a statistical curiosity. They were witnessing a break, a fracture, in what was supposed to be a cosmic mirror, and the crack was sharp. The algorithm that sees spin. But before diving into speculation, let's understand how spin is measured, because here's where human bias becomes a dangerous illusion. If you look at a spiral galaxy by eye, it's tempting to label its direction based on instinct, but our brains, brilliant as they are notoriously biased. Right-handed people tend to see right-handed spirals more easily. Cultural reading direction affects interpretation. Even the interface of software tools can nudge outcomes without anyone noticing. So to sidestep this mess, the JWST team used a tool called Ganalyzer. It doesn't think, it doesn't guess, it just measures. How Ganalyzer cracks the spiral code. Ganalyzer works like this. It takes the image of a galaxy and slices it radially from the center outward, like cutting a pizza into hundreds of thin rays. Along each ray, it records the brightness of pixels, creating a radial intensity plot that maps how light curves away from the center. Then it tracks where the brightness peaks occur and how those peaks drift as you move around the circle. If the peak brightness drifts in one direction, the slope is positive, that's one-handedness. If it drifts the other way, the slope is negative, that's the opposite spin. Ganalyzer doesn't care if you're left-brained or right-handed. It follows math, not mood. And crucially, when you flip the galaxy image horizontally, the measured spin flips too. That means the method is symmetric by design, just like the universe is supposed to be. But when it was applied to the 263 spiral galaxies from JWST, the mirror broke. The crack is real. 158 galaxies spun one way, 105 the other. Even when adjusting for uncertainties, image quality, distance and morphology, the asymmetry remained. It wasn't noise, it wasn't an artifact, it was embedded in the light itself. And here's the strange part: this kind of imbalance had shown up before. Years earlier, ground-based telescopes had hinted at a dipole pattern, a cosmic preference for one spin over another across vast regions of space. But those findings were often dismissed as unreliable, potentially skewed by poor resolution or subjective labeling. But JWST isn't blurry. It's the sharpest eye we've ever pointed at the early universe. And it just confirmed what many hoped or feared wasn't real. The mirror doesn't just have a hairline fracture, it's splitting. The problem with preference. Let's say the asymmetry is real, that the cosmos truly prefers one direction of spin. That would mean the universe violates parity symmetry, the idea that the laws of physics are the same in a left-handed or right-handed coordinate system. That's a bold violation. The only known example of this happening is in the weak nuclear force, where certain particle decays show a clear-handedness. But now, galaxies? Vast swirling cities of stars and gas showing preference on the largest scales we've ever studied? That's like finding out the entire chessboard is tilted, not just one piece. And it raises a terrifyingly elegant question. What if the whole universe has a spin? A hidden rotation? Cosmologists have speculated about universal rotation for decades. A slow, large-scale, swirling motion of space-time itself. In standard cosmology, the universe expands but doesn't rotate. There's no axis, no cosmic up or down, but there are models exotic but mathematically sound that allow for it. Bianchi cosmologies, for instance, describe universes that shear, twist, and tumble through time. In these models, rotation leaves behind fingerprints, subtle alignments in the cosmic microwave background, preferred directions in galaxy clusters, and yes, spin asymmetries in deep-field galaxies. Could JWST be seeing one of these fingerprints? Could this be the first real evidence that the universe isn't just expanding, it's spinning? Or is it us? But before we jump into rotating universe theories, there's another possibility, one far closer to home. What if the spin bias isn't in the sky, but in the mirror itself? We live inside the Milky Way, a spiral galaxy, spinning on its own axis. We observe the cosmos from within that motion, and that means our entire perspective is tilted. Light coming from galaxies rotating in the same direction as the Milky Way might appear slightly different than light coming from galaxies rotating in the opposite direction, especially if relativistic effects like Doppler boosting or brightness selection play a role. If this is true, then our galactic mirror isn't flat, it's curved, warped, and everything we see is already skewed. The mirror shatters further, but even accounting for this, even modeling for Milky Way rotation, for Doppler effects, for bias in galaxy visibility, the asymmetry remains. And that's the haunting part. It's not enough to explain the numbers. Something deeper might be happening, something fundamental, because symmetry, when it breaks, leaves behind a trail. And if we can follow that trail, we may find the truth buried beneath the cosmic reflection. Maybe the universe we see isn't the whole story. Maybe we're trapped inside something, looking out from behind the glass. For over a century, cosmology has been built on a quiet but powerful assumption that the universe, on its grandest scales, is isotropic. It means this: no direction is special. Look left, look right, peer into the north or the southern skies, fly to the edge of what's observable. The laws of physics, gravity, thermodynamics, quantum mechanics should greet you the same way every time, like a fair judge in a cosmic courtroom. This is not just a poetic idea, it's the foundation of modern cosmology. And now, thanks to a peculiar twist in the light from ancient galaxies, that foundation is starting to shake. The cosmological principle, our first agreement with the universe. The cosmological principle, the idea that the universe is both homogeneous and isotropic on large scales, is the quiet heartbeat of every Big Bang model. It tells us the universe has no center, no edge, no favored directions or locations. In simpler terms, wherever you are, and whichever way you look, the universe should look the same if you zoom out far enough. This principle gave us equations. Those equations gave us predictions. Those predictions gave us cosmic microwave background maps, galaxy distributions, supernova redshift curves, all of which seem to confirm the fairness of the cosmos. But fairness is fragile, and when Webb reported 158 galaxies spinning one way, 105 the other, that fairness was called into question. Symmetry on trial. This spin asymmetry isn't about one or two galaxies twisting oddly. It's about a statistical skew large enough to be visible to the naked eye and significant enough to survive algorithmic scrutiny. If this pattern is real and not the result of bias or selection, then it's more than a curiosity. It's a violation of isotropy. It means the universe may have a preferred direction, a cosmic left and right, a secret axis. It's as if, after centuries of thinking we lived in a boundless ocean, we've suddenly felt a faint current, a flow, suggesting that this ocean has shores after all. The ripple effects of anisotropy break isotropy, and everything else begins to wobble. Your distance ladder, the way astronomers measure the size and age of the universe, assumes that redshifts behave the same in all directions. Your inflationary model's theories of how the universe exploded into being assume perfect symmetry in the quantum fluctuations that seeded galaxies. Your dark energy estimates, cosmic variance equations, even your interpretations of the cosmic microwave background all depend on the idea that the sky is unbiased. If there is even a subtle preferred direction in galactic spin, it implies that the universe may have inherited angular momentum from an earlier phase. Light and matter might propagate differently along different axes. Cosmic structures could be entangled across distances we thought were causally disconnected. That's not just fascinating, it's destabilizing. Deep field dipoles, a pattern emerges. This isn't the first time the cosmos has flirted with anisotropy. In 2012, 2016, and again in 2024, different teams using Hubble, Subaru, and ground-based surveys noticed small-scale handedness imbalances galaxies spinning preferentially in certain parts of the sky. Each time, critics pointed to classification noise, annotator bias, field selection issues, and even weather patterns during telescope operation. But now, JWST has entered the game, and its data, from a cold, quiet spot near the galactic South Pole, shows the same twist. With sharper resolution, with algorithmic labeling, with infrared clarity, the dipole, a lopsided axis of spin, persisted. It wasn't strong enough to rewrite textbooks, but it was strong enough to whisper, "This isn't random, the sacred versus the observed." There's a painful tension here between what physics demands and what the sky delivers. On one side, the elegance of theory, on the other, the stubbornness of observation. Scientists are trained to respect symmetry. It gives birth to conservation laws. It simplifies equations. It makes the universe readable. But nature doesn't always respect our desires for beauty. And sometimes, it plays with loaded dice. Could the universe itself be slightly lopsided? Could we be watching the ripple of a hidden cosmic rotation buried beneath billions of years of expansion? Or are we being deceived not by the universe but by our perspective? Frame-dependent reality, a dangerous illusion. Let's remember, we're not neutral observers. We're sitting inside a galaxy. That galaxy is spinning. That spin creates a rotating frame of reference. And just as Einstein taught us that observers moving at different speeds experience different time and space, perhaps observers spinning inside a galaxy see different versions of cosmic spin. It's possible, even likely, that our Milky Way introduces frame-based distortions in how we classify distant galaxies. Subtle Doppler shifts, brightness asymmetries, light-bending effects that skew our counts just enough to fool us. If galaxies rotating opposite to the Milky Way appear brighter or more defined, we might be overcounting them without realizing it. In this case, the asymmetry is not in the universe, it's in our window. But even if that's true, it still teaches us something profound. We are not outside the cosmos. We are within it, and our motion shapes what we see. What would it take to break isotropy for real? To challenge a foundational pillar like isotropy, scientists need more than anomalies. They need replication from multiple surveys, using different instruments across many sky regions. They need to ask, do we see the same spin imbalance in other fields far from the galactic poles? Does the asymmetry persist across different wavelengths and exposure times? Do results from Roman, Euclid, and the extremely large telescope agree with JWST? If the answer to all those is yes, then the sky itself might be revealing a hidden structure, a cosmic fingerprint older than time. If not, we'll know the crack in the mirror was ours. Either way, we learn something priceless. The shattered mirror, an invitation. A crack in isotropy doesn't mean the universe is broken. It means it's more complex than we imagine. It could be the echo of a rotating parent universe. It could be the trace of a hidden topological twist. It could even be the signature of a black hole cosmos, where our entire universe spins within the horizon of something larger. For now, we don't know, but what's certain is this. The sky no longer smiles the same in every direction. It twists. It whispers. It invites us deeper. Light doesn't age like we do. It travels. It waits. It remembers. When the James Webb Space Telescope opened its eye and stared into the abyss, it wasn't just collecting data, it was listening to whispers. Whispers from galaxies so far away, their light left before Earth even existed. Galaxies that spun and shimmered when the universe was still young, a mere toddler, just 4 or 5 billion years old. And in those whispers, it heard a secret. The twist, the spin asymmetry was there, too. It didn't start recently. It wasn't local. It was ancient. The message in the light. Every photon that Webb captures is a time traveler. A single galaxy in the Jade Survey part of the good South Deep Field might be 9, 10, even 13 billion light-years away. That means we're not seeing it as it is today. We're seeing it as it was near the dawn of time when the first stars were still igniting, when cosmic dust was coalescing into structure. And in those deep reaches, the pattern emerged. More galaxies spiral in one direction than the other. The ratio wasn't random. It wasn't noisy. It was sharp. 158 clockwise, 105 counterclockwise. And it didn't matter that these galaxies were scattered across cosmic distances and evolutionary stages the imbalance held. The cosmos, from its youth, already had a twist, structure in the chaos. You might expect the early universe to be messy. After all, the Big Bang was chaotic, a flash of energy, a burst of inflation, a soup of particles that cooled into stars and galaxies over billions of years. Surely any spin should have averaged out. Equal chaos in all directions, random orientation, no memory of a beginning. But that's not what we're seeing. What if spin isn't an accident? What if angular momentum, the tendency of things to rotate, is not just a local feature of galaxies, but a cosmic inheritance, an ancient rhythm laid down in the first seconds after the Big Bang or whatever came before? Birth of a spiral. Let's zoom in. Galaxies don't just emerge as spirals. They're shaped over time by gravitational collapse, dark matter scaffolding, and the push-pull of tidal forces. But angular momentum is part of that birth. Even a tiny rotational bias, at the earliest stages, a small tilt in the fabric of space can snowball. The spin of a proto-galactic cloud, influenced by nearby overdensities and the curvature of space-time, can determine whether it becomes a clockwise or counterclockwise spiral. It's like dropping thousands of marbles into a bowl. If the bowl is perfectly flat, the marbles scatter randomly. But if the bowl has a slight tilt, a preferred slope, even one you barely notice, the marbles will roll in one direction more than the other. The cosmos may have a slope, and galaxies have been rolling down it for 13 billion years. Redshifted truths. JWST doesn't just see farther, it sees earlier. By detecting infrared light stretched by cosmic expansion from its original shorter wavelengths, Webb reveals galaxies that Hubble and ground-based telescopes could never resolve. In this way, it's a time machine. A portal, a voice recorder for the early universe, and the message it's playing back is unsettling. The asymmetry in galaxy spin is stronger the further back we look. That suggests it's not just a local effect, not just Milky Way bias, not just Doppler tricks. It's cosmic history, written in the spiral arms of ancient galaxies, echoes of an ancestral motion. Here's where things get eerie. The asymmetry seems to increase with redshift, a measure of how far away, and thus how old, the galaxies are. This could mean that the preference for one direction of spin was more dominant in the early universe and has become diluted over time, like ripples in a pond fading as they expand, or like the slowing spin of a great cosmic wheel that once turned faster long ago. And if that's true, we're staring at something profound, a memory of motion, not random, but inherited, not recent, but primordial, the fossil in the frame. Some cosmologists now wonder whether galaxy spin direction could serve as a kind of fossil record, a tracer of early universe conditions, like tree rings that preserve droughts or ice cores that record volcanic ash. Unlike temperature or brightness, which fluctuate and blend, handedness is binary. It can't be smoothed away. A galaxy spins left or right. It doesn't forget. So if there was a global angular momentum laid down in the earliest moments of creation, perhaps even before inflation spin might be our only clue. And now, that clue is speaking. In JWST's crystal clear vision, the fossil is glowing, one side brighter than the other. Galactic polarization? Some have even floated a radical idea that spiral galaxies act like polarizers, aligned in a way that reveals the orientation of space-time itself. If so, spin direction isn't just a property of the galaxy. It's a signal, a reflection of something bigger, something embedded in the geometry of the universe. A vast polarization, a twisted space-time, a cosmic gyroscope pointing to what? A rotating parent? A hidden dimension? A black hole? We don't know, but the very fact that these questions now seem plausible, that the data demands them, tells us how far we've come. A whisper that might become a scream. For now, the handedness asymmetry is still a whisper, a single deep field, a few hundred galaxy. But science begins in whispers. The cosmic microwave background started as static. Dark energy began as a faint tension in supernova curves. Exoplanets started as starlight wobbles. Everything begins quiet, until the data multiplies, until the sky gets mapped, until the symmetry or its fracture becomes undeniable. And if that happens, then this whisper from ancient galaxies may become the loudest scream in cosmology. We study the universe as observers. But what if we're not just observers? What if we're participants in the illusion? As strange as it sounds, our view of the cosmos is not neutral. It is shaped, colored, and warped by the very place we're observing from. A spinning, glowing, electrically active spiral galaxy known as the Milky Way. It's easy to forget that we're trapped inside one of these swirling giants, our sun just one dot among hundreds of billions. But here's the danger. When you live inside the machinery, sometimes you mistake its noise for the voice of the universe. And now, with JWST's discovery of a spin asymmetry in distant galaxies, we must ask a disturbing question. Is this the voice of the cosmos? Or the echo of our own shadow? The problem of perspective. Imagine standing in a hall of mirrors. Every wall reflects you, but slightly warped. No matter where you look, the image you get is filtered through your position. That's the predicament of astronomy. We don't get to drift above the galaxy and observe from the outside. We're locked inside it, moving, rotating, and wrapped in a cocoon of dust and magnetic fields. That means everything we see is affected by where we are and how we're moving. We don't observe the cosmos from a God's eye view. We observe it through a moving, spinning telescope mounted to a moving, spinning planet inside a moving, spinning galaxy. That matters more than you think. The galactic rotation bias. Our Milky Way spins. It's a spiral galaxy, just like the ones JWST has been observing. Its arms trail in a particular direction. From our position tucked about 27,000 light-years from the galactic center, we experience that spin firsthand. We're rotating at around 828,000 kilometers per hour, carried by the disk as it turns. Now picture this. You're inside a spinning carousel, watching fireworks explode all around you. Some appear to streak past faster, others seem slower. Some appear brighter, some dimmer, not because they're different, but because you are moving. That's relativity, and it applies to light from galaxies too. If a distant galaxy is rotating with the Milky Way, its light might appear slightly different than if it's rotating against us, even if the galaxy itself hasn't changed. Doppler shadows and brightness traps. Rotation introduces relativistic Doppler effects. Galaxies whose spin is aligned with our motion may appear slightly dimmer or blurred, while those spinning in the opposite direction might be brightened by Doppler boosting. This can create a false pattern in the data, making one direction seem more prevalent than it really island. Not because the universe is biased, but because our view island. This is the Milky Way bias hypothesis, a leading counter-explanation for the spin asymmetry seen by JWST. It doesn't deny the data. It doesn't accuse the algorithm. It simply suggests that we're seeing through a funhouse mirror and mistaking its distortion for a cosmic truth. Galactic foregrounds and frame effects. Beyond brightness, there are foreground effects. The Milky Way contains enormous clouds of gas and dust, especially near the galactic plane. That's why surveys often focus on the poles, the top and bottom of the galaxy, where there's less obstruction. But even there, the rotation of our galaxy might introduce systematics. Imagine a camera lens that spins as you take photos. The blur, the distortion, it's not in the subject, it's in the frame. Cosmic surveys rely on assumptions, that photons travel straight, that they're unbiased by intervening matter, that the telescope is a passive collector. But what if the frame itself is twisted? What if the Milky Way, with its electromagnetic fields, gravitational influence, and motion through space, subtly tilts the statistics, nudging the numbers ever so slightly, enough to turn randomness into illusion? Statistical smoke, physical fire? Critics of the spin asymmetry point to this very possibility. They argue, if the asymmetry disappears in fields located elsewhere far from the galactic South Pole, then it's a local artifact, not a universal truth. The JWST field is near the pole. If spin preferences reverse or vanish in fields near the galactic North Pole or in orthogonal regions, that would suggest the Milky Way's geometry is to blame, not the universe itself. This is testable, it's falsifiable, it's science, working the way it should. But here's the catch. Even if the effect is frame-based, it's still revolutionary, because it means our galaxy is not just a participant in the cosmos, it's a lens, a bias engine, an active filter on reality. And that's a truth we rarely account for. The observer is never separate. In physics, we're taught to treat observers as external, objective, detached. But quantum mechanics taught us something else, that the observer matters. That observation isn't passive, it's an act. It influences outcomes. Now, cosmology may be facing the same reckoning. The Milky Way isn't just a backdrop. It's the frame through which we measure the very laws of nature. And like a rotating clock influencing the time it tries to record, it may be embedding its own motion into the universe we think we're measuring. If that's true, then the cosmos is not a fixed canvas. It's a painting we're inside of, brush in hand shaping as we stare, modeling the shadow. To correct for this, scientists need more than better telescopes. They need frame-aware cosmology models that explicitly account for the observer's motion, rotation, and location. They need to model how the Milky Way's spin influences photon paths, how frame-dragging effects might tilt detection algorithms, how even gravitational lensing might encode rotational memory, and perhaps how to subtract the Milky Way's shadow from the light of the universe itself. Because only then, only when we remove our own fingerprints, can we know what the universe truly looks like. And only then can we ask the next, deeper question: what if the bias remains, even after the frame is cleared? Ghosts in the mirror. If future surveys from Roman, Euclid, ELT, and beyond confirm that the spin asymmetry persists even far from our galactic frame, then we're dealing with something far more profound, something cosmological, something primordial. And if that's the case, then the Milky Way's shadow wasn't fooling us. It was pointing at something deeper, a real twist, a hidden axis, a cosmic fingerprint that no local bias could create. We would then have to ask, where did that spin come from? And what kind of universe could give birth to a cosmos? With a preferred direction? The answer may lie not in the galaxy we live in, but in the structure we live inside of. It began as a whisper, a strange imbalance in a patch of sky, then another, then another. Each time, the numbers were too small to be trusted. Each time, critics waved it off as noise, coincidence, or bias. But now, in the wake of JWST's spin asymmetry, 158 clockwise, 105 counterclockwise, that whisper has returned. Louder, sharper, and behind it, something darker is beginning to take shape. A shadow, a hidden alignment, a ghostly axis that seems to stretch across the sky, not visible to the eye, but statistically real. Is the cosmos trying to tell us where forward is? Mapping the cosmic dipole. In physics, a dipole is a pattern with two extremes, a push and a pull, a left and a right, a here and a there. We've seen dipoles before. The cosmic microwave background, the oldest light in the universe, has one. It tells us we're moving at about 600 kilometers per second relative to the early universe. That motion creates a hot side and a cold side in the CMB sky. But what's happening now isn't temperature, it's spin. Across different sky surveys, Hubble, Subaru HSC, even ground-based projects, researchers have noticed that galaxies in one half of the sky spin more clockwise, while those in the opposite half lean counterclockwise. And when plotted, the asymmetry doesn't look random. It looks like a dipole, an arrow, a direction, a pattern that deepens with distance. What makes this axis so eerie isn't just its presence, it's its depth. In studies that stretch across different redshifts from relatively nearby galaxies to those billions of light years away, the spin imbalance grows with distance. Closer galaxies, roughly balanced. Mid-range galaxies, slight tilt. Deep field galaxies, a clear preference. This gradient implies something terrifyingly elegant. The asymmetry isn't local, it's cosmic, and it may have been seeded at the very beginning of time. As if the Big Bang didn't just explode outward, it twisted, and that twist left a scar, a cosmic grain, a preferred direction in the loom of space-time, the axis that won't die. Physicists have a nickname for these kinds of anomalies, the axis of evil, originally coined in reference to the strange alignments found in the cosmic microwave background. The phrase now haunts multiple observations. Dipole alignments in supernova brightness, large-scale velocity flows, the polarization of quasars, and now, spiral galaxy spin. Each of these findings might be dismissed on its own, but together, they trace a phantom line across the sky, not one the eye can see, but one that survives the math. It cuts across constellations, it pierces the heavens, and now, with Webb's data, it seems to be reaching back all the way to the early universe, echoes in other surveys. Before JWST, the asymmetry was first seriously proposed by researchers studying Sloan Digital Sky Survey, SDSS, data finding thousands of spiral galaxies, showing a non-random distribution of handedness. Later, Hubble Space Telescope deep fields hinted at the same. Then came Subaru's HyperSuPrimeCam, HSC, observing different patches of sky with better resolution, where a similar trend appeared. None of these were conclusive. All of them were debated. But now that JWST, the sharpest instrument humanity has ever built, is finding the same imbalance, the possibility of a real, persistent, directional pattern becomes harder to ignore. It's as if every telescope was brushing past the same ghost. And now, we're finally looking it in the eye. Skepticism, the guardian of truth. It's important to say this. Science doesn't leap to conclusions. Every new axis, every claimed asymmetry, is met with fierce skepticism. That's not weakness, that's strength. False patterns are easy to see in noisy data. Randomness loves to masquerade as structure. Even human pattern-seeking, our psychological bias, can deceive us. That's why methods like GANalyzer, CNN-based classifiers, and mirrored pipelines exist to eliminate the artist's brush from the analysis. Yet, even with all of that, the asymmetry remains, which leads us to an uncomfortable possibility. Maybe the universe isn't perfectly isotropic. Maybe symmetry isn't the rule, it's the illusion. And maybe we're starting to see the grain of the cosmos. What would an axis mean? If this ghost axis is real, not an error, not a trick, but a structural truth, what does it mean? It would mean the universe isn't directionless. It would challenge the cosmological principle, the idea that the universe has no preferred center, edge, or orientation. It would force us to reconsider the initial conditions of the Big Bang, the geometry of space-time, the possibility of a rotating universe, the idea that our cosmos was born with spin, and that has consequences, because a rotating universe isn't just different, it's foundationally different. It changes how matter clumps, how time flows, how expansion unfolds, and most radically, it might hint that we're not just living in the universe, we're living inside something else. The black hole connection. One of the wildest implications of a rotating universe is that it might resemble the interior of a Kerr black hole, a rotating solution to Einstein's equations. In such a model, the universe is not expanding into nothing, it's expanding within the event horizon of a larger reality. Inside this spinning black hole, space and time behave differently. There is a preferred axis, there are swirling flows, and time doesn't move straight. The spin asymmetry could be a fossil echo of that rotation, a leftover fingerprint from a cosmic ancestor. And this ghostly dipole might be the scar tissue from that birth, the road ahead. But no ghost can be confirmed with a single sighting. To prove this axis is real, we'll need independent sky patches far from the galactic poles, multiple telescopes, JWST, Roman, ELT, Euclid, multi-wavelength analysis from radio to X-ray, spectrokinematic confirmations, not just morphology but motion. Cross-survey dipole fits to see if the axis holds across time, space, and methods. Only then can we say, this is not noise, this is the spine of reality. And perhaps the first clue that we're not in a blank void, we're in a structure, and it might be spinning. We've been told that the universe plays dice, that the early cosmos, born in fire and quantum chaos, unfolded by chance, its galaxies scattered like seeds on the wind, their directions, spins, and positions shaped not by purpose, but by probability. Randomness has long been our fallback explanation. If we don't understand it, if it doesn't fit, we say, it's just random. But randomness is not a blank check. It has rules, it has limits, and sometimes it breaks. Because when you toss a coin 10,000 times and it keeps landing on heads, you don't need another toss, you need a new theory. The statistical battlefield, the spin asymmetry spotted by JWST, is small 158 galaxies clockwise, 105 counterclockwise. But in statistics, small numbers can whisper big truths if the deviation from expected values is sharp enough. In an isotropic universe, we expect spiral spins to be a fair coin toss, 50/50, plus or minus a little statistical noise. But this isn't noise. This is a 50% excess of clockwise galaxies. And when you repeat that finding across multiple fields, multiple telescopes, and multiple decades, randomness begins to collapse under its own weight. Still, some scientists push back. They argue, it's within the margin of error. It's a selection effect. It's an artifact of method, not reality. That's not denialism. That's discipline. But as the evidence accumulates, one thing is becoming clear. Randomness is running out of excuses. The role of reproducibility? In science, reproducibility is the holy grail. One finding means nothing. 2 is a coincidence. But 3, 4, 5, across instruments, methods, and teams, then the game changes. That's what's beginning to happen with galaxy spin. A growing number of surveys, Hubble, Subaru, SDSS, JWST, are pointing to the same quiet asymmetry. Not identical, not overwhelming, but persistent. Even when the datasets are cleaned, even when the algorithms are swapped, even when the galaxies are mirrored, randomized, anonymized, the imbalance doesn't go away. It's as if randomness is trying to play fair, but keeps getting pulled by a hidden weight. And that weight is starting to look real. The skeptics speak. Still, many voices in the astrophysical community urge caution. They point to flaws in earlier analyses, biases introduced by image labeling, inconsistent galaxy classification, selection thresholds that eliminate ambiguous spirals, the possibility of citizen science contamination, where humans unknowingly introduce bias into datasets. All of these are valid concerns, and yet, that's exactly what the JWST team addressed. They used Ganalyzer, a fully symmetric algorithm that mathematically determines spin without human labels. They tested the tool by flipping images, and it produced inverted results, proving its neutrality. Even under these strict controls, the spin asymmetry persisted. Skepticism is healthy, but when it starts defending a randomness that no longer fits, it stops being caution and starts being resistance. When chaos hides a pattern, one of the greatest lessons from 20th century science came from chaos theory. It taught us that order can emerge from apparent disorder, that swirling hurricanes, economic booms, and even the growth of trees can arise from deterministic processes hiding beneath randomness. Could cosmic spin be the same? Could what looks like chance a tilt here, an imbalance there be, the signature of a hidden order, a faint algorithm, a rotational fingerprint, a whisper from the universe's blueprint? If so, then we're not looking at noise. We're looking at structure wearing a mask, the cosmic coin toss. Let's reframe the problem. Imagine a room full of physicists. You give each one a fair coin and ask them to flip it 263 times, just like the number of spiral galaxies in the Jade sample. You'd expect each result to hover around 50 over 50, maybe 140 heads, 123 tails, or 132 and 131, fluctuations but small. Now, imagine someone walks in and says, "I flipped 158 heads and only 105 tails." Wouldn't eyebrows rise? Now imagine that same imbalance starts appearing in other rooms, other coin tossers, other buildings. Wouldn't you start to question whether the coin is really fair? That's what's happening in astronomy right now. And the coin might be rigged, a pattern that grows with time. Perhaps most alarming is this: the spin asymmetry doesn't just exist. It seems to grow stronger the further back we look in time. At low redshifts nearby galaxies, the spin balance is nearly even. But at high redshifts in the ancient universe, the imbalance becomes pronounced. That shouldn't happen. If it were noise, it should stay constant. If it were a local effect, it should fade with distance. But here, it does the opposite. This suggests a cosmic gradient, a large-scale directional influence that becomes more obvious the deeper we look into the past. And that's not randomness, that's history. History with an orientation. If galaxies formed in a rotating, anisotropic environment, if the very early universe had a twist, then spin is a kind of historical record. Not metaphorically, literally. Each galaxy is a spinning fossil, preserving the angular bias of its birth environment. When enough of them lean the same way, it tells us the twist wasn't local. It was baked into the cosmos. And if the asymmetry is strongest at the greatest distances, the earliest epochs, then we're looking at something primordial, something born at, or even before, the Big Bang. And that means randomness is no longer enough. The dice have fingerprints. What if we're wrong? Let's be clear. The the burden of proof is still enormous. It could still be an illusion, a statistical quirk, a cosmic coincidence. But let's ask, what if we're not wrong? What if the asymmetry is real? What if randomness has failed us? Then the consequences are staggering. The universe has a preferred direction. The Big Bang may have occurred within a rotating frame. The large-scale structure of the cosmos is not isotropic, and perhaps we are living inside a rotating entity, a black hole, a higher dimensional structure, a parent universe with spin. Whatever it is, it's not random. It's orchestrated, and we've just begun to hear the music. For over a century, we've imagined the universe as a silent expansion, a smooth balloon inflating in nothingness. No spin, no swirl, just outwards. But what if we were wrong? What if the universe doesn't just expand? What if it spins? A vast, imperceptible rotation so slow, so smooth, it escaped every eye. Until now, because deep in the light of ancient galaxies, in the subtle imbalance of their spiral arms, we may be hearing the first faint echoes of a rotating universe. What happens when the cosmos spins? To imagine a rotating universe is to abandon comfort. In the standard cosmological model, the universe has no preferred direction. Every axis is equivalent. There is no cosmic up, no down, no master clock to tick against. But if the universe spins even slightly, that symmetry shatters. Suddenly, there is a cosmic axis, a north and south, a pole of motion. Rotation warps space-time. It bends geodesics. It drags the fabric of reality in the direction of its twist, a phenomenon known as frame dragging, proven near Earth by satellites like Gravity Probe B. Now imagine that on a universal scale, not just stars being pulled by rotation, but space itself being twisted like a cosmic whirlpool. Enter the Bianchi models. Einstein's equations don't forbid a rotating universe. They allow it in special cases known as Bianchi cosmologies. These are solutions where the universe can shear, tumble, twist, and swirl as it expands. In Bianchi Type 7, H models, for instance, the universe rotates slowly on a large scale while still obeying general relativity. These models predict subtle anisotropies, tiny imbalances in the cosmic microwave background, density fluctuations, and, yes, even galaxy spin alignments. They're not mainstream, but they're mathematically legal, and for decades they were ignored. Why? Because we never had evidence that the universe preferred a direction. Until now, a compass hidden in the light, the spin asymmetry reported by JWST, confirmed by earlier hints from Hubble, Subaru, and SDSS, could be the very fingerprint these models predicted. A faint cosmic compass embedded in galactic spin. If galaxies formed in a universe already rotating, their angular momentum wouldn't be random, it would be biased. Not because of local collisions, but because the fabric of space itself was turning. Over billions of years, that spin would be fossilized in the rotation of galaxies. And now, we might be seeing that fossil, not in one place, not in one field, but across time and sky. Why would the universe spin? That's the deeper question. If the universe spins, what set it spinning? Spin, or angular momentum, is conserved. It doesn't just appear, it has to be inherited. So, what came before the Big Bang? Here's where theory tips into the surreal. Some physicists believe that our universe is not the beginning, but the interior of something larger, a structure born not in emptiness, but in collapse, a black hole cosmology, inside the event horizon. In a theory first proposed in the late 20th century and explored more deeply in recent decades, some cosmologists suggest that what we call the universe is actually the interior of a black hole. In this view, the Big Bang isn't the origin of time, it's the moment of entry, when matter collapsed through an event horizon and inflated into its own space. And if that parent black hole was spinning as real black holes do, then the interior universe would be born with a built-in axis of rotation, a direction, a twist, a hidden compass in space-time. Exactly what the galaxy spin asymmetry seems to suggest. The Kerr black hole connection, This idea finds roots in the Kerr solution, the exact mathematical description of a spinning black hole in general relativity. Unlike non-rotating Schwarzschild black holes, Kerr black holes have frame dragging. They pull space-time along with their spin, ring singularities, replacing the central point with a ring-like region, ergospheres, regions where nothing can remain stationary, dragged by the rotation. Inside a Kerr black hole, the structure of time and space twists much like what some cosmologists predict for a rotating universe. If our cosmos is the interior of a Kerr-like black hole, it would naturally have a preferred direction. It would expand, yes, but also carry an ancient rotational memory, one we may now be detecting. Predictions of a rotating cosmos. A rotating universe wouldn't just affect galaxy spin, it would leave signatures everywhere. Anisotropies in the cosmic microwave background, alignment of quasar polarizations across billions of light years, dipole patterns in dark matter distribution, time dilation, effects along different cosmic axes, correlated spin alignments among galaxy clusters, and the most elegant prediction of all, that the deeper we look, the stronger the twist. That's exactly what JWST is showing us. In the farthest galaxies, the spin imbalance grows, randomness fades, symmetry decays, and rotation emerges. From theory to testable hypothesis. None of this is fantasy anymore. We now have the instruments JWST, Roman, Euclid, ELT to test these ideas. We can map galactic spin across the entire sky, compare opposing fields, flood dipole, test Bianchi models against observed data, search for consistent CMB anomalies aligned with galaxy spin vectors. If the patterns hold, the case strengthens. If not, the axis fades and the mystery deepens. Either way, we win insight, a universe with memory. If the universe spins, then it remembers. It carries an echo, a direction, a thread woven through 13.8 billion years of cosmic history. It means the Big Bang was not a perfect explosion. It was a twisting birth, a moment of motion, not just expansion. And it may mean we are not in an infinite, empty cosmos, but in the swirling interior of something deeper, something we've only begun to understand. It sounds like science fiction, the kind of idea whispered in late-night forums or scribbled into notebooks by dreamers. What if we're living inside a black hole? Not orbiting one, not near one, inside one? A whole universe, ours, unfolding not in empty space, but within the event horizon of a far vaster reality. And now, for the first time, real data may be nudging us toward that radical possibility, because the cosmic spin imbalance revealed by JWST, the subtle preference in galaxy rotation, could be more than an anomaly. It could be a clue, a gravitational fingerprint, a rotational scar, the signature of a universe born from collapse, not from nothing. A black hole is not what you think. We picture black holes as cosmic drains devouring stars, swallowing light, ending time. But that's only half the story. Mathematically, the interior of a black hole isn't a void, it's a region of space. It has geometry, curvature, evolution, and in the case of a Kerr black hole, a rotating one, the inside is far stranger still. There is no central point. Instead, there's a spinning ring singularity, a tunnel of distorted space-time that warps the rules of causality. Some solutions even allow for passage not to another place, but to a new, expanding space. Sound familiar? It should, because that's what our universe looks like. Expansion from collapse. The Big Bang is often described as an explosion from nothing, but in truth, it was an expansion of space, not into space. There was no outside to burst into. Now consider this. The equations describing the interior of a rotating black hole bear an uncanny resemblance to those describing an expanding universe. Inside the event horizon, space must expand. It's baked into the math. Time and space swap roles. There's only one direction left to move forward, outward, just like our cosmos. The idea then is this. What we call the Big Bang was actually the moment a massive star collapsed in another universe, forming a rotating black hole. and giving birth to a new universe within. Ours, a universe with spin. If the parent black hole had angular momentum, its interior would inherit a preferred direction. That spin would manifest subtly not as a tornado in the sky, but as a bias in the way matter forms, clumps, and rotates. Over billions of years, that cosmic twist could influence the handedness of spiral galaxies, the polarization of light across vast distances, the alignment of structures on scales larger than expected. And now, with the Webb telescope's discovery of a spin imbalance in ancient galaxies, that faint rotational imprint may have finally been seen. Not proven, not confirmed, but glimpsed like the silhouette of a giant through a swirling fog. A second time, a second space. Black hole cosmology suggests something even more radical. That time itself may start over, inside a black hole. Outside the event horizon, time ticks forward. Inside, it's warped, stretched, and ultimately reborn. This gives rise to a wild but mathematically sound concept, that the collapse of matter in one universe can create an entirely new space-time region with its own clock, its own space, and its own physical laws. It's not magic. It's relativity pushed to its limits. In this view, our universe isn't the only one. It's part of a lineage, a cosmic genealogy, where black holes become cosmic wombs. And our spin, our galaxy's orientation, the strange imbalance seen by JWST, that might be our umbilical cord, the last thread connecting us to whatever came before. What the critics say, this isn't a mainstream idea. Not yet. Most cosmologists still lean toward traditional Big Bang models. No spin, no parent, no black hole ancestry. Why? Because the evidence is still thin. The models are complex, and the concept of a universe inside a black hole feels dangerous. It flirts with metaphysics. It tempts philosophical questions that science prefers to sidestep. But as our data gets better, as instruments like JWST, Roman, and ELT unveil the fabric of the early cosmos, in high definition, the door to these radical ideas slowly creaks open, and with each new anomaly, each asymmetry, each axis, each whisper of rotation, the ground beneath the old models begins to shift. The cost of staying comfortable. Science progresses not by clinging to comfort, but by confronting contradiction. We believed Earth was the center of the universe until Copernicus challenged the sky. We believed space was absolute until Einstein bent it into curves. And now, perhaps, we believe the Big Bang was the beginning because the alternative is just too wild. But what if the real wildness is refusing to look? What if our universe is not the grandest structure, but a subsystem? Not a standalone cosmos, but an interior region of something greater? And what if the galaxies, spinning just slightly more one way than the other, are trying to tell us that story? Signs of the black hole origin. If the black hole hypothesis is true, there should be signs. Clues hidden in the structure of space and the behavior of light. Here's what scientists are looking for. Dipole alignments across multiple cosmic datasets. CMB, anisotropies that can't be explained by standard inflation. Galaxy spin correlations across opposing sky fields. Breakdown of isotropy at high redshift. Gravitational wave signatures from a birth by collapse scenario. And perhaps someday, evidence of time asymmetry. A one-way arrow inherited from a rotating collapse. If those signals align, the black hole model moves from metaphor to mechanism, and the story of our origin becomes stranger and more beautiful than we ever imagined. The most important question. But let's ask the question that matters most. Why does this idea feel so terrifying? Why do we recoil at the thought that we're living inside a black hole? Maybe because it flips the hierarchy. It humbles us. It makes our entire universe a side effect, a region, a consequence. But maybe that's exactly what makes it meaningful. Because if our universe was born from the death of another, if we're the flame born from a collapsing star, then we are part of an eternal cycle, not a beginning, but a continuation. A cosmic breath, drawn in collapse, exhaled into space and time, and we spinning gently in the darkness, are the children of a deeper gravity, We speak of telescopes as if they're divine instruments, machines of pure truth, piercing the veil of the cosmos. But every eye, no matter how advanced, sees through something: a lens, a method, a filter, an assumption, and in the case of JWST's shocking discovery, the subtle imbalance in galaxy spin, we must ask not only what we're seeing, but how we're seeing it, because the universe may not be hiding its secrets. We may be looking through a distorted mirror and calling it a window. The truth doesn't just depend on the sky. It depends on the eyes we use in the dark, the machinery of vision. The James Webb Space Telescope is a marvel, an origami of gold and mathematics folded into the vacuum of space. Its cameras are tuned to infrared, allowing it to see galaxies at the edge of time. Its resolution can capture spirals smaller than a whisper in the dark. Its mirrors reflect light that began its journey when the Earth was still molten rock. But JWST doesn't label galaxies. It doesn't say this one spins left or that one spins right. That's our job, or more precisely the job of our algorithms. And therein lies the paradox. We're trying to detect cosmic asymmetry with tools that may have biases of their own. When humans label the sky, early galaxy spin studies used citizen scientists, ordinary people, trained to look at images and classify spirals. It was beautiful, democratic, inclusive. Millions of galaxies were sorted by human eyes, creating massive datasets for research. But humans aren't neutral. We're pattern-hungry, culturally wired, right-handed, left-dominant, subconsciously influenced by the direction we read, the screens we use, even the tools we hold. Studies showed that volunteers tended to classify more galaxies as right-spinning, even when images were mirrored. This isn't malice, it's the human lens. And so, to detect real patterns in the universe, we had to step aside and let machines see for us. Enter the Ganalyzer. One of the most influential tools in this space is called Ganalyzer. It's not an AI. It doesn't guess. It calculates. Here's how it works. Take a galaxy image. Slice it radially from the center, like cutting a pizza. Measure the brightness along each slice. Analyze how those brightness peaks drift as you go around. Determine whether the arms trail clockwise or counterclockwise based on that drift. Ganalyzer flips the image, remeasures, and checks for symmetry. If the result inverts, the method is sound, and that's exactly what the JWS team did. The result? Even with perfect symmetry in method, the spin asymmetry persisted. 158 clockwise, 105 counterclockwise, and the mirror still cracked. The rise of neural eyes. But now, a new generation of observers is emerging. Artificial intelligence, deep learning systems, convolutional neural networks, CNNs, algorithms that don't just measure, they learn. These systems are trained on thousands, even millions of galaxy images. They extract features the human eye can't see. They classify spin with stunning speed, but they also learn our biases. If the training data is unbalanced, say, it contains more clockwise galaxies, the AI may carry that preference forward. If the labeling was done by humans, even subtly skewed, the machine absorbs those errors as if they were truth. And worse, we don't always know what it's learning. Neural networks are powerful, but often opaque. They can detect structure, but they can also hallucinate it. The observer's dilemma. This is the observer's dilemma in the age of cosmic data. If we trust humans, we risk subconscious bias. If we trust machines, we risk silent distortion. If we trust math, we risk missing nuance. If we trust nothing, we see nothing. And so, paradoxically, the more advanced our tools become, the more we must question their output. We don't just need eyes in the dark, we need eyes with accountability. That's why modern spin studies rely on cross-validation, comparing different methods, different algorithms, even different types of data, morphology versus kinematics. Because if multiple methods agree, if symmetric rules and neural networks both see the same twist, then maybe the asymmetry isn't in the algorithm, it's in the cosmos. When the method matches the madness, in the JWST study, The Ganalizer algorithm produced the asymmetry. A separate CNN trained on previous labeled datasets found a similar trend. These tools don't speak the same language, yet they told the same story. 158 to 105. A consiste de préférence. From different instruments, different samples, different rules. That convergence matters, because when two eyes see the same ghost, one biological, one artificial, you have to ask, is the ghost real? Or are we all just hallucinating the same shape? The shadow of confirmation. Here lies the next frontier of caution. Even if multiple tools see the same asymmetry, we must ask, was the data independently selected? Were the images pre-processed with the same assumptions? Were the algorithms trained on overlapping datasets? Confirmation bias can creep in not just through individuals, but through entire research cultures. An entire field can tilt slowly, subtly toward the result it most expects. That's why some scientists call for double-blind classifications, hidden datasets, randomized image flips, balanced training samples. Only through such discipline can we be sure the twist isn't in the method, but in the sky, zaying beyond ourselves. At its core, this isn't just a technical problem, it's a philosophical reckoning. We are no longer lone astronomers with hand-drawn charts. We are engineers of algorithms, orchestrators of silicon minds, using machines to gaze where our eyes can't follow. And in doing so, we've stepped into the quantum of cosmology. The observer shapes the observed, not just in quantum labs, but across the stars. To see the truth of the universe, we must first confront the filters of our own vision and ask, honestly, are we seeing the twist in the galaxies? Or in ourselves? The universe has spoken, but only in a whisper. A twist in a single deep field. A pattern in one patch of ancient light. But a whisper is not a verdict. It's a beginning. If this asymmetry is real, if galaxies are spinning more one way than the other, then it's not enough to hear the signal from one corner of the cosmos. We must map the whole sky, because only a full view can answer the most important question in modern cosmology. Is the twist local, or is it everywhere? The limits of a sliver. The Jade's deep field where JWST detected the 158 versus 105 spin imbalance is a cosmic postage stamp. A slice of sky so small, you could cover it with a grain of sand held at arm's length. It was chosen for its clarity, not its representativeness. Near the galactic South Pole, it's clean free of Milky Way dust and clutter. But that's also what makes it dangerous. Because if the asymmetry is only present there, it may be a field-specific artifact caused by observational geometry, local structure, or even biases in detection algorithms near the pole. To test the reality of the twist, we must go beyond the sliver. We need the full dome of the heavens, the mission of 1,000 eyes. Over the next decade, a new generation of telescopes will scan the sky with unprecedented depth and breadth. Together, they form the mapmakers of the modern age. Nancy Grace Roman Space Telescope, NASA. Launching soon, Roman will survey the sky in wide-field infrared. Its high-latitude survey will cover over 2,000 square degrees orders of magnitude more than JWST's field. With Roman, we'll be able to identify spiral galaxies across large, diverse sky regions, compare spin directions in opposite hemispheres, detect potential dipole or quadrupole asymmetries in spin distribution. Roman won't just add to the data, it will test the symmetry of space itself. Euclid, ESA, already in space, Euclid is scanning 15,000 square degrees to study dark energy and cosmic structure. It will provide imaging and spectroscopic data on billions of galaxies, including morphology, orientation, and clustering. With Euclid, we can confirm the spin alignment across redshift layers, cross-match with JWST and Roman fields, test whether spin preference correlates with cosmic voids, filaments, or dark matter flows. Subaru Prime Focus Spectrograph, PFS. On the ground, Subaru's upcoming PFS will collect data from both hemispheres, critical for testing north versus south asymmetries. It will provide high-quality spectroscopy, allowing us to measure actual rotation curves, not just morphology, a powerful cross-check against image-based spin classification. Extremely Large Telescope, ELT. Once operational, the ELT will give us unparalleled resolution, capable of resolving spiral structure in faint, distant galaxies that today appear as smudges. With that power, we can measure spin in early galaxy clusters, detect whether galaxies formed in alignment with large-scale structure flows, push the spin signal to higher redshifts closer to the Big Bang. Together, these instruments form a symphony, a chorus of perspectives, and their combined vision will either confirm the twist or silence it. The test of field independence. One of the core tenets of scientific validation is field independence. If an effect is real, it should appear in multiple regions of the sky, across different telescopes and wavelengths, using independent methods of classification. That's the challenge ahead. We must analyze spin orientation in the northern galactic hemisphere, the southern galactic hemisphere, regions aligned and misaligned with the Milky Way's axis, deep fields and wide surveys, near and far redshifts. If the asymmetry persists, especially if it aligns along a consistent cosmic axis, the implications will be undeniable. But if it reverses or disappears in certain areas, we'll know the twist was not in the sky, but in the window, a cartography of spin. Imagine the future, a spin map of the observable universe. Each spiral galaxy marked not just by its location and distance, but by its direction of rotation. Left, right, clockwise, counterclockwise. Across millions of dots, patterns emerge. Dipoles, gradients, tidal flows. Perhaps we'll find regions where spins are aligned like wind-blown trees. Perhaps we'll see the twist fade with time or strengthen near the cosmic edge. This would be more than a map. It would be a fingerprint, the signature of how the universe was stirred at birth. A new coordinate system? If the asymmetry proves real and persistent, we may need to redefine how we describe the cosmos. Currently, we use celestial coordinates based on Earth's equator, or the plane of the Milky Way. But imagine this, a new axis, not based on our rotation, not tied to our galaxy, a cosmic spin axis, defined by the orientation of galaxies across billions of light years. We would then have a new reference frame for the universe, a tool to re-express cosmic microwave background data, a benchmark for testing early universe models with angular momentum. In short, a cosmic north, one that's not about where we are, but about how everything began. Risks and rewards? Of course, mapping the sky won't guarantee revelation. We may find that the spin asymmetry disappears at scale, that it's an illusion, a glitch, a mirage. That's the risk. But the reward? If the pattern holds, if the twist is everywhere, if the map reveals an embedded swirl in space-time, then we will have pierced the veil of the Big Bang. We will have touched the prelude to time, and will be forced to rewrite everything from inflation to dark energy to the origin of the cosmos itself. The map and the mirror. The sky is no longer just a background. It's a canvas of code, a mirror that reflects not just where we are, but what we're inside of. A map of galaxy spin isn't just astronomy, it's ontology. It's about whether space has a direction, whether the universe has memory, whether we are the children of symmetry or the descendants of a twist. We've called it the beginning, the Big Bang, the ultimate origin story. A moment when time and space erupted into being, carrying all matter, energy, and law in one cataclysmic burst. No before, no cause, just a singularity, followed by expansion. But what if that story isn't complete? What if the Big Bang wasn't a singularity, but a transition? Not an explosion from nowhere, but a spin-out from something deeper, something larger, something that remembers. Because when galaxies spin unevenly across the sky, when the universe itself seems to carry a directional bias, we must confront a possibility no textbook dares to linger on. What if the universe began already turning? The myth of the perfect beginning. The standard model of cosmology paints a beautiful picture. An infant universe, hot and dense, expands rapidly in an inflationary burst. Quantum fluctuations stretch into galaxies. Matter and antimatter annihilate, photons decouple, and the cosmic microwave background cools into a whisper. But this picture is also sterile. There is no direction in this model, no spin, no memory, just smoothness, randomness, symmetry. And for decades, it worked. It predicted the CMB spectrum, large-scale structure, and cosmic nucleosynthesis with astonishing precision. But now, spin has entered the scene, and with it, the entire model may need to evolve. A universe born with angular momentum. Angular momentum is everywhere. Planets spin, stars rotate, galaxies twirl, clusters drift in vortices of dark matter. But where does that spin come from? Conservation laws demand that angular momentum must be inherited, passed down from larger scales, or present from the very beginning. If the universe started with no net angular momentum, all these motions must have emerged from local fluctuations. But if the entire cosmos shows a statistical preference in spin like JWST now suggests, then that spin might be primordial. In other words, the Big Bang may have been rotating. A rotational bang. What does that mean? Imagine the universe as a ballerina. In the standard model, she stands still, then leaps outward. But in the rotational model, she's already turning before the leap. Her arms, galaxies spin out with her. The dance has orientation, not just motion. This shift changes everything. It means inflation may have occurred with a spin axis, not uniformly in all directions. It suggests cosmic structures aligned not randomly, but along a preferred swirl. It implies parity violation on cosmological scales, left and right no longer interchangeable. It transforms the Big Bang from a pure expansion into a dynamical spiral, and that spiral could be the very source of the asymmetry now surfacing in our deep field observations. From symmetry to structure, in early universe physics, symmetry breaking plays a key role. The primordial plasma cooled and chose a configuration like a spinning top that falls in one direction. That breaking gave rise to forces, particles, even the structure of matter itself. But what if rotation was a part of that choice? What if, alongside the Higgs field and inflation, the early universe selected a direction of spin, a cosmic chirality, a universal handedness? Then the spin asymmetry seen by JWST wouldn't be an accident. It would be a fossil of that decision preserved in the way galaxies spiral billions of years later. Inflation with a twist. Most inflation models assume perfect isotropy. Expansion smooths everything equally. But there are alternative models, lesser known, but mathematically valid, where inflation occurs in a Bianchi-type universe, rotating, shearing, or anisotropic. In these models, expansion doesn't erase the spin. It dilutes it, yes, but traces remain. And those traces? They show up as alignment of quasar polarizations, dipole anisotropies in the cosmic microwave background, handedness asymmetry in spiral galaxies. Sound familiar? These aren't just theoretical coincidences. They're observable predictions, and they're starting to appear in the data. Maybe inflation didn't erase rotation. Maybe it stretched it into visibility. The geometry of a spinning start. In general relativity, rotating spacetimes are described by metrics like the Gödel or Kerr solutions. These geometries allow for frame dragging, closed time-like curves, directional horizons, global rotation without a center. While such metrics are extreme, they prove one thing. The laws of physics allow for a rotating cosmos. They don't demand it, but they permit it. And now, with signs of asymmetry, alignment, and dipole structure across cosmic time, perhaps we're seeing the geometry of the beginning. Not a point, not a flame, but a whirl, time, space, and the twist. If the universe began with spin, time itself may carry that rotation. In quantum field theory, certain particles remember their chirality. In a spinning universe, perhaps time acquires such chirality, an arrow not just of entropy, but of orientation. We often ask, why does time move forward? But perhaps a better question is, what direction is forward in a rotating universe? Could the arrow of time itself be twisted, its flow shaped not only by entropy, but by a cosmic rotation field? Could this be the key to solving the matter-antimatter imbalance, the CPT problem, or even the cosmic baryon asymmetry? If the universe spun from the start, then time, matter, and space may all bear the same imprint, the death of nothingness. This isn't just about cosmology, it's about narrative. The Big Bang has long been framed as a beginning from nothing, a magical explosion from a singular point. But what if that's a story we told to avoid what came before? A rotating universe doesn't just start. It emerges from curvature, from collapse, from another space. It demands a prior, a mechanism, a womb, and it reintroduces causality not as a chain of effects, but as a spiral, a loop of motion through which new universes spin out of dying ones. It turns the origin story from a myth into a process, a new genesis. If the Big Bang was a spin-out, if the universe carries an inherited axis, if galaxy-handedness is not random, but ritual, then the cosmos isn't a blank slate, it's a memory machine, and our existence, this entire moment, is not the beginning. It's the next chapter, the continuation of an ancient motion, a rhythm, a twist. We are not the children of nothing. We are the children of angular momentum. There's a question at the heart of every mystery we've uncovered so far. Is the universe twisted, or is it just our perspective that's bent? Because for all our instruments, all our data, all our telescopes peering across time, we are still inside the machine. We are not floating outside the cosmos, looking in. We are not neutral. We are embedded, spinning, drifting, living inside one spiral galaxy, the Milky Way, trying to understand the infinite by peering through a keyhole. And in doing so, we must face a deeper truth. The observer is not separate from the observed. Einstein's shadow. Einstein taught us that the speed of light is constant, but everything else depends on where you are and how you move. Time dilates, lengths contract, mass changes. Your perspective shapes your measurement. Two observers can see the same event and disagree on when it happened or how far it occurred, and both be correct. This wasn't philosophy, it was physics, and it set the stage for something even more radical. Maybe reality itself isn't universal. Maybe it's frame-dependent. Now imagine that principle applied not to objects, but to the entire cosmos. Our cosmic trap. We live in the Milky Way, a vast spiral galaxy spinning at nearly 1 million kilometers per hour. We orbit its center. We revolve around our sunday. We stand on a rotating Earth. And every observation we make, every photon we catch from deep space, is filtered through this moving, twisting, gravitationally complex frame. This is not a minor detail. It means that everything we see is warped by our velocity, our orientation, our position within gravitational fields, the interstellar medium of our galaxy, the rotational motion of the Milky Way itself. So when we look up and see that galaxies far away appear to spin more one way than another, we must ask, is that the sky's truth? Or our illusion? The inescapable lens. There is no cosmic outside, no Archimedean point, no place to stand and view the universe objectively. Every perspective is a local lens, and the Milky Way is not a clean window. It is a warped mirror. Its dust clouds obscure and redden light. Its magnetic fields distort polarizations. Its motion introduces Doppler effects, boosting brightness from one side and dimming the other. Its structure creates systematic biases in survey strategies, favoring cleaner regions, skewing field selection. Even the angle at which galaxies appear to spin can shift subtly, depending on where we are, how we move, and how we classify. The observer's frame is everything, and yet it is also invisible. Quantum echoes. In quantum mechanics, the observer plays an infamous role. The outcome of a measurement depends on the act of observation. The wave function collapses not randomly, but in relation to the system and the observer's setup. Some call it interpretation, some call it mystery, but the principle remains. You can't remove the observer from the equation. Cosmology may now be facing the same reckoning, not in the quantum realm, but on the grandest scale imaginable. What if the direction of the universe's spin, the asymmetry we think we see, is shaped not only by the cosmos, but by us, the observer's illusion? There are 3 possibilities. The spin asymmetry is real. The universe has a preferred axis. Something fundamental is being revealed. The asymmetry is local. A structure in our vicinity, a supercluster, a filament, a void is skewing the data. The asymmetry is frame-induced. The motion, spin, and bias of our own position in space are painting a false pattern on the sky. Each has profound implications. But the third is the most unsettling, because if it's true, then we're not just misinterpreting the cosmos, we are encoding our presence into it, seeing ourselves in the sky, mistaking the mirror for the window. Can we escape our frame? Is it possible to correct for the observer? Yes, to an extent. Astronomers use redshift correction for our motion relative to the CMB, frame transformations in data processing, mock simulations to model observational effect, instrumental calibration across sky surveys, statistical symmetry tests like flipping, mirroring, and rotating galaxy images. But these methods still begin with our location, our sensors, our sky. We can test for biases. We can reduce them, but we can never fully erase ourselves from the equation. We are part of the experiment, and the universe knows it. A new kind of objectivity. What if objectivity doesn't mean erasing the observer, but understanding the observer's influence? That's the new frontier. To see clearly, we must map not just the sky, but our frame inside it. A full cosmological model must now include the rotational dynamics of the Milky Way, the relativistic effects of our motion, the gravitational warping of our local structure, the biases introduced by our algorithms and instruments. Only then can we hope to distinguish the true cosmic asymmetry from the echo of our own spin. Why it matters? This isn't just about precision, it's about truth. If we mistake a frame effect for a fundamental law, we rewrite the story of the universe on a lie. But if we correct for the frame, and the asymmetry still remains, then the universe is speaking in a voice no longer masked by our motion, and what it says could redefine the origin of time, the nature of space, the architecture of cosmic birth. Because if spin remains after the observer is accounted for, it is no longer illusion, it is law, reflections in the void. We used to think the universe was out there, waiting to be seen, but now we know better. The universe is not just something we observe, it is something we participate in. We shape what we see not by choice, but by presence. And the spin we detect may be more than a twist in galaxies. It may be a message, a cosmic palindrome. You are not the center, but you are never separate. What if the cosmos isn't silent? What if, beyond the glowing nebulae and cold voids, beyond the equations and models, something deeper moves? A rhythm, not just expansion, not just entropy, but a pulse, a hidden tempo beneath the noise of stars, a beat to which galaxies twist, space-time flows, and time itself unwinds. Because if this universe truly spins, if there is a preferred direction, a handedness, a bias in the breath of the cosmos, then maybe we are not living in chaos, but in a pattern. Maybe the universe has a heartbeat, and we've only just begun to hear it. From explosion to oscillation, the Big Bang was once imagined as a single moment, a burst, a flame, a singular scream into silence. But spin changes that. Spin implique duration. Spin implies continuity. Spin implies rhythm. The act of turning is not an event, it's a process. And if the universe was born rotating, then perhaps time itself is not linear, but cyclical in some hidden way. Not in the sense of repeating events, but in the sense of motion with memory. A turning cosmos is not just a place that moves. It is a place that remembers how it moves, and that memory becomes a pulse, a universal signature woven through time. The spiral as symbol and structure. Why do galaxies spiral? Because they are born of spin, because gravity dances with motion, because structure forms where momentum and matter embrace. But maybe spirals are more than structure. Maybe they are echoes. Look closely. The Nautilus shell, the hurricane, the sunflower, the golden ratio in galaxies and leaves, the spiral arms of DNA, the whirlpool of water, the shape of time in ancient mythologies. It's everywhere from the smallest particles to the largest galaxies. A spiral is the shape of a dynamic system with memory. It is nature's way of saying, I do not return, but I do remember. And if the universe is a spiral on the grandest scale, then it, too, remembers. Cosmic music. Pythagoras once said, the cosmos was music, the harmony of the sphere's celestial bodies singing as they move. Modern science dismissed that as metaphor, but maybe it was prophecy. A rotating universe may carry modes like vibrations in a drum. Spin could create resonances across space, standing waves in the cosmic field. Could this explain the periodicity of galaxies? The oscillations in the cosmic microwave background? The strange alignment of quasar polarizations? We don't know yet, but we are beginning to ask. What is the frequency of the universe? What is the beat of the void? Time as a spiral. We think of time as a straight arrow, but perhaps it's a spiral staircase. Each moment moves forward, but also around. Each rotation adds not just progress, but perspective. In this model, history never repeats, but it echoes on the pace. Evolution is not a line, but a spiral of memory and growth. Consciousness doesn't ride time like a train, it climbs it like a spiral tower. If the cosmos began with spin, then time itself may be twisted, not broken, not looping, but coiled. And perhaps that coil explains why time feels directional, even though the laws of physics don't require it. Spin gives time a handedness, a heartbeat, consciousness in the spiral. Let's go further. If reality is rhythmic, if space and time pulse, then what is consciousness? Is it an emergent computation? A spark from neurons? Or is it resonance? A dance between observer and pulse? We know the brain oscillates in alpha waves, gamma bursts, theta rhythms. We know perception is structured around cycles. What if we are tuned to the universe's rhythm, not metaphorically, but physically? What if consciousness is a phase-locked loop with the cosmos? A way for the spiral to become self-aware? Spin as meaning. We look at handedness in galaxies and see data, but maybe it's also language. A universal chirality left and right woven into the code of reality. From particle physics to DNA, handedness shapes what is and what can be. In a mirror world, the same atoms might not bind, the same molecules might not form. Now, imagine that on a cosmic scale, if the universe has a dominant spin, a global chirality, it might determine not just physics but possibility. It might select which structures emerge, how complexity unfolds, what kind of life can arise. Spin, then, is not cosmetic, it is ontological. It is the choice between being and not being, the beat before the bang. Let's entertain the unthinkable. What if the Big Bang wasn't the first beat? What if it was the second? What if before our expansion began, there was a collapse, a spiral drawn inward, curving tighter, accelerating into density, until it spun outward again, not in destruction, but in rebirth? This is the black hole hypothesis, yes, but it is also something older. Many ancient cultures envision time not as linear, but cyclical, not as a line, but a drumbeat, not as a wall, but a breath, expand, contract, spin, repeat. Maybe science is now finding poetry in its equations. And the heartbeat we're detecting is not just the universe's, but our own. The rhythm of becoming. Everything pulses. Atoms vibrate. Hearts beat. Stars flare. Galaxies rotate. Universes expand. And in all of this, perhaps there is not chaos, but rhythm, a cosmic syncopation that underlies reality itself. The galaxies twist not in silence, but in time, to a beat. And maybe, just maybe, if we learn to listen, we'll discover that we've been dancing all along, You followed the twist, from the soft glow of spiral galaxies turning in the abyss, to the unsettling possibility that our universe prefers one direction over another, to the poetic, speculative, and controversial idea that we might be living inside a cosmic vortex, the rotating interior of a black hole. Now we arrive at the final question. What do we do with this? What does it mean for science, for philosophy, for us, if the cosmos is not neutral, not balanced, not perfectly ambidextrous, but tilted, handed, biased, alive, the left-handed sky, 158 clockwise, 105 counterclockwise. That's what the James Webb Space Telescope found in a deep, ancient corner of the sky. A simple count, but numbers, when precise and persistent, can shake the foundations of belief. This asymmetry, small yet stubborn, dares to whisper, the universe has a spin. It's not proof, not yet, but it's a signal, a crack in the glass of isotropy, the assumption that no direction is special, no axis is privileged, no frame of reference is sacred. If that crack widens, if the signal holds across time and space, then physics will have to answer a hard question. What happens to the cosmological principle when the cosmos picks a side? The fragile throne of symmetry. Our understanding of the universe is built on pillars, homogeneity. Every place is the same on large scales. Isotropy. Every direction is the same. Lorentz invariance. The laws of physics don't care how fast you move. Parity. Left and right are equal, a mirror is as good as the original. But in nature, symmetry is often broken. The weak force violates parity. Matter outnumbers antimatter. DNA twists only one way. Most people are right-handed. Hurricanes spin opposite in different hemispheres. So, why should the entire universe be immune? Why should we assume the cosmos is perfectly fair? Maybe fairness is not fundamental. Maybe bias island. Maybe existence itself emerges from a broken symmetry, a coin that landed ever so slightly on its edge. The spiral as identity. In a mirror world, your heart would beat on the other side. But in this one, it beats leftward. And that's not trivial. Handedness shapes life. It shapes chemistry. It shapes reality. And now it might shape cosmology. If the universe favors one kind of twist clockwise over counterclockwise, that choice may ripple outward into the formation of structure, into the distribution of angular momentum, into the early conditions of inflation, even into the possibility of life. Because if the spiral is biased, then the pattern is not random. And if it's not random, it may be telling us something. Black hole? White truth? Let's entertain the boldest version of the theory. Let's say this asymmetry is real. Let's say it traces all the way back to the moment of creation. Let's say we are living in the rotating interior of a parent black hole, a Kerr cosmos. What then? Does that explain everything? No, but it would rewrite the story of the Big Bang. It would suggest that the singularity was not a point, but a vortex. Time didn't begin, it spilled into being. Space isn't expanding into nothing, it's unwinding from a center. The arrow of time is not a one-way road, but a spiral staircase. And we are passengers riding that twist born of momentum, cradled in curvature, destined to loop the loop of a cosmic pulse we're just beginning to hear. Evidence, skepticism, and wonder. But science is not fantasy. It is the fire that tests metal, not the spark that lights dreams. And so we must be clear, this handedness anomaly could be real, or it could be a selection bias. It could be a system artifact, or it could be noise. Only time will tell. But what matters now is the question. Because great revolutions in thought, Copernicus, Einstein, quantum mechanics didn't begin with answers. They began with someone noticing something strange. A wobble, a shadow, a count that didn't add up. So let's not look away. Let's look deeper. Let's look harder. The mirror in the sky. The cosmos may not be symmetrical, but maybe neither are we. We are biased. We are shaped by perspective. We are trapped in the gravity of our assumptions. And when we look up, we see ourselves in the symmetry we crave, or the chaos we fear. But maybe the universe is not chaos. Maybe it is character. It has texture. It has memory. It has rhythm. And maybe that rhythm chose a direction. Left, right, it doesn't matter. What matters is that it moved. And it moved us. In the end, the numbers are simple. 158 clockwise. 105 counterclockwise. But behind them lies a mystery profound enough to humble science, awaken philosophy, and stir poetry. Are we just watching galaxies spin? Or are we seeing the shadow of something bigger, a cosmic breath, a forgotten symmetry, a fingerprint of a deeper structure? Maybe we are not just in the universe. Maybe we are of it, wound into its spiral, aligned to its pulse, spinning together toward a truth still unnamed. And maybe, just maybe, this black hole we fear was always home